First. Hi guys, again, and welcome to Physics 10. Today is March 23rd. We have a lot of topics to cover, so I'm going to start basically sharing the screen. We have basically 3 topics in one. You will see that there is a common themes in them. That's why actually I connected them. It's about solids, liquids, and gases. So, okay. So let me share the screen. And it's this one. Okay, very good. So again, there are 3 topics, as I said. I put them together because there is some commonality. As a matter of fact, if you look at the content, you will see that these things repeat. I mean, the pressure in liquids and pressure in gases are identical. The buoyancy also is in both of them. Archimedes Principle applies to both of them. What makes objects sink and float, that is actually also common, but you see it more in liquids than in gases, because of the fact that it's much easier to float something over a liquid than over a gas, but it's also, objects can float in gases, case in point, the balloons, okay? So, and then we're gonna talk about Pascal's principle, which is also common to both of them. Since we're talking about the states of matter, there are actually, these are the 3 states of matter that we have experience with on a daily basis, namely solids, liquids, and gases. And the 4th phase of matter is plasma, actually. That is actually another case where the matter is completely ionized. So this is the item of the discussion that I want you to really be clear about. The 4 states of matter are basically the topic of the day: solids, liquids, gases, and plasma. Okay. Solids is basically things that are rigid, they retain their shape, basically. So whatever shape you have, they retain it. Liquids, they don't retain their shape, and they occupy whatever basically is a below, they change their shape basically, but they're not also compressible. There are some properties that we're going to come into. Gases, on the other hand, they occupy the space that you give it to them. So these are the 3 differences in them. Plasma is kind of a weird thing. I mean, if you think of fire, for example, when you light matches, that is the state of plasma. That is basically the fire that you see in there. It's the state of ionizations, when objects are completely ionized. So they lose some electrons, they lose 2 electrons, and because of that amount of energy involved, that is what you see in terms of flames. So this is a topic number 1 of discussion. And also, I want to ask you guys, what do you think is the most common in your intuition? What is the most common element that you have experience with, or what do you think the universe is mainly made up of?
Is that part of the question, or you want us to answer that?
No, this is now, okay? The question is that you have to identify the 4 basic forms of matter that is known in the universe. The 4 knowns of matter are, again, solids, liquids, gases, and plasma state. Not the plasma that biologists talk about for the blood and all of that. That is not what I mean by it. Think in terms of matches, for example, when you light a fire. That is probably more appropriate to it. Or lightning when it strikes. If you saw that, that is actually plasma too. So, in terms of what you think the main form of matter in the universe is it option 1, solids, option 2, liquids, option 3, gases, or option 4, plasma?
You said in the universe?
In the universe, everything combined, yes.
Gases.
Yes.
So somebody's
Gases.
A couple of gases, okay. How about solids and liquids? No?
Guess
There's
not.
a huge, but there's a huge amount of fluid. I mean, in the earth, there's a lot of water on the earth, and a lot of rock. No? Nobody? So I want you to put the answers in there because I want to see it. This is not democracy, by the way. Everybody has to tell me something. One of these 4, of course. Okay, Marco is wondering maybe, is that a question or is that an answer, Marco? Ah, an answer. Marco thinks it's plasma. So it's mainly fire? Is that what you're saying? Okay, Raquel thinks it's gas. I want to ask Marco, why does he, I mean, like, everybody, there is a consensus, seems like gas wins it, okay? But for some reason, okay. So you guys don't give a chance for the materials like solids, for example, that we have everyday items of? No? Okay. I have somebody else taking liquids, thinking of water and all kinds of liquids. Okay, so it's still gas is winning it by a big margin. Okay, somebody finally dead. Okay, so Marco now is thinking big. Can you think that maybe Marco has a point in here, guys? Because he's making the case that the sun is mainly plasma, isn't it? And since the sun is 99% basically of the entire solar system, so what you guys talking about in terms of solids and liquids and gases, they're dwarfed by the amount of plasma that is actually in the solar system. Does his argument make sense? Is that what you're saying first? I know I saw it. Okay, now you have somebody who's converted to your thinking, because that doesn't sound. Is that what you're saying, Marco, first? I put it in my own words. Probably that's what you had in mind, because it says, doesn't the sun contain plasma? Yes? Okay, very good. So now it seems like at least one person, another person has joined Marco in a sense, thinking that maybe plasma, after all, is the main dominant form of matter in the universe. Yes? You guys agree? Okay, so you have more winners now. It seems like more people are joining you. Okay, let me tell you something, okay? Okay, so more and more people now, okay. It seems like plasma is probably the #1 form of the universe. If you think in terms of the solar system, okay? If you think that the stars out there, they're still dominating their neighborhood, and stars are mainly plasma. Okay? It's mainly fire, basically. Ionized hydrogen gas and helium, basically. That's what star is, mainly. So it's really, it looks like it's plasma is the #1. However, don't ignore gases yet. The interstellar space between them is mainly hydrogen, albeit very, very low density, but it's still hydrogen. So gas is probably, if it's not #1, it's very close number 2. So that is basically the competition between the two. So solids, unfortunately, and liquids, they don't come anywhere near. Okay, these two big fundamental forms of matter. As a matter of fact, the dominant element in the universe is hydrogen, whether in the plasma form or gas form. It makes up more than 75% of matter in the universe, is hydrogen by itself, protons basically, whether in the plasma form without the electrons or with their own electrons in the interstellar space in the form of gases or something like that. Combined with, later on comes in helium, which is the almost 25%, and the rest, which is negligible, all of the rest of the elements in the periodic table. So this is what we're talking about in here. Unfortunately, here on Earth, we don't see that. We see mainly solids, basically, on a day-to-day basis. We see liquids with in a lot of forms, and also we see gases, okay? We see gases. Gases and liquids are classed by themselves called fluids. So that's why a lot of these laws that apply to liquids, they apply also to gases, because both of them have this fluid behavior. Both of them are fluids, as a matter of fact. So gases and liquids have that. Plasma also has fluid behavior too, albeit at extremely high temperatures, okay? Solids, on the other hand, have distinction between two types of solids. Solids that have a crystalline structure, like for example, salt, okay? Like a lot of minerals, they have crystal structure. In other words, they have periodic forms in here. I'm sorry, there is a repetition in their structure. There are crystals inside of it. There is a unit of them that is repeating over and over and over for an organized shape, more or less, okay? Salt has that structure, okay? And then there is another types of solids that are called amorphous solids. Those are solids that are actually behave more like very, very much like fluids because they flow, albeit extremely slow, okay? So that is basically the difference between the two, okay? This properties lead to a lot of properties of the solids themselves. Some of them have different ductile behavior, different basically how you're going to extend them, what happened to them, and elasticity, and so on and so forth. So this is basically what the topic of the day today is. Again, the crystalline structure, I just mentioned the fact that you have an organized, repeating pattern in and out, the way we investigated that by Röntgen and the people in the toward the end of the 19th century, and at the beginning of the 20th century, basically too, is where they shine X-ray radiation and they see that the refracted basically, or reflected, I'm sorry, radiation comes in with specific patterns, with specific interference patterns. Those interference patterns were indicating that there is a periodic structure in here, and the separation between the atoms or the constituents of the metal have very specific distances and very special arrangements for those crystals. So this is one of the features of solids, or at least a class of solids, because there is another class that does not show that, okay? Like glass, for example, is not a crystal. I mean, I know the word is used for it sometimes, but it is not a crystalline structure. As a matter of fact, it shatters when you break it, okay? It does not really, it's not ductile. It does not change. For example, if you take a piece of iron and you hit it with a hammer, it actually flattens and starts to get smoother and smoother. You can make a sharp knife out of it, but try to make the same thing with a big block of glass. When you hit it, it's going to shatter and scatter in every which way. Okay, so this is some of the properties, and it's coming from that property that you can change it. Anyway. Solids, they are held together by chemical bonding, which is really due to the interaction of the electrons, okay? So the chemistry in here is very simple to some extent, okay? So you have an atom on one side and you have another atom on one side. Each atom has its own electrons. So the interaction is due actually to the electrons only. So the inside of the atom does not participate. As a matter of fact, there are inner electrons in the inner shells that don't participate in that. Only the outside electrons, the valence electrons that are available for interactions, those are the ones that do participate in this process of connecting atoms together to make molecules and to make solids actually too. So in the case of the ionic binding, so one atom, for example, like sodium, gives up one of its electrons. So it becomes positively charged because it lost an electron, and now it's positively charged as an ion by itself. And in this case, because you have a net positive protons more than electrons, so the net effect is that it's positively charged. Chlorine on the other side has an affinity for electrons. It accepts electrons, it takes electrons, because its outer shell is just short one shy of an electron to fill it. So it has a very good affinity. Actually, all the halogens in the periodic table next to the noble gases, they have very high affinity for electrons, like, for example, chlorine in here, or fluorine above it, or whatever element that you have in there. So it takes an electron. Now, all of a sudden, its net charge is negative. So you have now sodium on one side positively charged, and chlorine on the other side negatively charged, and they are next to one another. So they attract one another by the fact that they are ions. One of them is positive and one of them is negative. So this is called an ionic binding, okay? They settle in a lower energy when they do that. And the salt, which is the result in this case, is a stable atom. As a matter of fact, a stable molecule. As a matter of fact, that molecule now, there is a rearrangement of those molecules one after the other. So there is a sodium on one side, ion, positively charged. Chlorine on next to it, which is negatively charged, attracting one another. On the other side of the chlorine, there is actually sodium. And on the other side of the sodium, there is chlorine. On the other side of the chlorine, there is sodium. And there is a repetition along this direction. There's also on this direction too. Sodium, chlorine, chlorine, sodium, and so on and so forth. And it's repeating also. So it's a 3D structure that assembles itself. And now you have an ionic structure of salt, okay, which is periodic structure, that is a crystalline structure. There is another type of a structure, which is covalent structure. Also, it's possible also in solids, where actually the atoms do not give up their electrons, but they share them instead. For example, carbon and carbon. Carbon has 4 valence electrons in the outer shell, and the other carbon also has 4 valence electrons. So instead of giving up an electron, both of them have the same power, both of them have the same level of affection for their electrons, so they share them instead. So this one shares its electron with the other atom, and the other one shares it in the middle. Okay. So now I have 2 carbons sitting next to one another, and another 2 carbons sitting next to one another, another 2 carbons sitting next to one another, and so on and so forth. Now already I have a crystalline structure that is made up of pure carbon, which is diamond. Okay. Graphite also has some sort of a crystalline structure, but graphite is laminar, which is basically the thing you write with, the pencil. Okay, that is graphite. Actually, do I have a pencil in here? No, I don't see it. So that is also similar. It has the same chemical structure. Both of them are carbon, but how you arrange the carbon, that's all that makes the difference between diamond and carbon. One of them has very, you can actually push it against a piece of paper, and it leaves its mark, and you use it for writing. And the other one is one of the strongest basically elements you use, for example, to break rocks when you're digging for oil and things like that. So again, this is covalent. So in this case, in this case, both of them share the same strength. Okay. This does not necessarily happen between similar atoms. It could happen with dissimilar atoms too. So, but in this case, there is that sharing of electrons. Okay. Then there is a van der Waals basically force. In this case, like what happened in some molecules, for example, water. It's polar in the sense that it is not completely ionic, and it is not completely covalent. What happened in this case? The atom of the oxygen will pull the electrons closer to it, whereas the hydrogen will more or less let go of its electrons, so that it doesn't really sit in the middle, but sits closer to the oxygen. Not completely captured by the oxygen atom, but near it. So the water molecule in this case is behaving like as if, and it's not really that strong, a dipole, meaning that there is a net charge next to the oxygen and a lack thereof, or a positive charge near the 2 hydrogen atoms, okay, or the H2O. Now this is fine, this is a molecule, but the way they arrange themselves when water becomes a solid, when it becomes ice, is the way that the oxygen comes near the hydrogen from the other atom. So now you have an H2O in one structure, another H2O next to it. So the atoms now, or the molecules, I'm sorry, rearrange themselves in such a way that the positive net side of the positive on one side, which is coming from the hydrogen, is lined up closer to the net negative side of the other one. So this is actually a weak force, okay? Because of the fact that the dipole in general is a weak force anyway, because it's really 2 charges, similar charges, are shielding one another to try to bind with other things. So this is basically of how that binding is happening. Sometimes when you have a dipole, it induces a dipole in the nearest atom and help one another to become stronger and stronger. Just like, for example, when you have a balloon and put it next on the wall, it's going to stick to the wall. This is an induction. It induces a dipole in the wall. It induces charges. There are no charges in there to begin with. So this is the van der Waals force. And now the metallic structure. The metallic structure is really a different thing altogether. So what it is that inside a solid, the atoms in this case have valence electrons that are available not just for that specific atom, but for the community of atoms. So in other words, now the atoms themselves, they're still neutral, but their outer shell of electrons now is shared for the entire community. So it looks like in a sea of electrons that are floating freely in a conductor, usually in metal, the ions, they are held in place by that sea, by that ocean of electrons in this case. So we call this one a metallic bonding, because again, it's true, first of all, for metals, because they are the ones who have electrons available to move. So they are in the valence and the conduction basically band, and they are available to move for heat transfer or for electrical transfer. So this is actually another way for bonding that is in metal. So again, this is how solids, at least in the crystalline structure, they behave. Clear? Yes? Good? Did any one of you take chemistry already in this class?
I did.
Okay, very good. This sounds familiar then. Okay, if you did not, okay, for those who did not, you probably will. So this should be more or less coming close to what you're going to be. Although in chemistry, at least in the chemistry that most of the time is offered in colleges, it's still in the first few years, it doesn't get into the solid structure and all of that. It really deals with the atom and then maybe the molecules, which all of this bonding except in addition to another bonding in there. In the case of the molecules, that doesn't show up in here. Anyway, this is plenty for right now. The other bonding is the hydrogen bonding, and that is basically by sharing protons themselves. And this is usually for organic chemistry, okay? For molecules, that is, but not for solids. Anyway, one of the properties of solids, it's their density. Each material has its own specific density, and that is how much mass is contained in a specific volume. Density, by definition, is mass over volume. It is a good reference to remember the density of water is 1,000 kilograms, or a ton, metric ton, that is, in a cubic meter. So if you think of this room, for example, and open wide your hand, not completely wide, okay? Don't do it, okay? Slightly like this much. That is about a meter, roughly, okay? So if you open it this way, that is a meter squared. And if you open it that way, that is another meter squared. In this volume, if you were to wear water, cubic meter is actually a ton. It weighs like a car, metric ton. It's a lot, about 2,000 pounds, okay? Another way of thinking of the density of water, because it's a good reference, it's a good number to look at because it's a round number. If you don't have to remember decimal points or anything like that. If you take a liter of water, which is really a regular bottle that you carry with you to go and running and jogging and all of that, that is about 1 kilogram. So 1 liter, it's not mentioned in here, 1 liter weighs exactly 1 kilogram. Or 1 gram weighs one cubic centimeters, which is a very tiny, weighs a gram. So those are round numbers for water. Now, density of our materials are different. For example, the air in this same cubic meter weighs 1.29. Water weighs 1,000 times more than air for the same volume. Obviously, if I fill this room with air, it weighs more than a kilogram of a liter of water, because this room has more air in it than a liter of. So this depends on the volume too. But in the case, if I take the same amounts one by one, air has a density which is 1,000 times less than that of water. Iron, on the other hand, is about 8 times heavier than water. It weighs about 7,800 kilograms for each cubic meter, whereas water is only 1,000. Okay? Aluminum, which is actually denser than water, but also less dense than iron, is about 2,000 something. Okay, a little over twice the weight of the iron. Okay. So these are some of the things. Wood, for example, is less dense than water. Okay, so now it becomes oil, for example, weighs less than water. As a matter of fact, ice weighs less than water, and that's why the icebergs, they stick their nose up of the water, although 90% of the iceberg is below the water, 10% of it is above, and that is because the density of actually ice is about 900 grams per cubic centimeter, per cubic meter. So it's just below this number for ice. That's why it floats. About 90% of it is still under the water though. So this is basically some of the ideas in here. But for solids in general, this is actually a good measure. So if I'm measuring the density of an element and I don't know what it is, if I find the number, I can go and consult the numbers in there and I see Is it too big? If it's too big, maybe more than 7,000. Maybe it could be lead. Lead has super high density. Copper has also huge density compared to iron. One of the densest elements out there is actually gold, and then uranium, which is super dense material. Okay, so these are stuff that we can explore through density. So it's a very important concept. So density depends upon the mass of the atom, spacing between the atoms. So how the atoms are arranged in the material. So how they are packed is critical in here, okay? So how much mass can you put in a given volume? That is basically what the density is. Elasticity is one of the properties of materials, also solids. Basically, if you take a, what happened to my spring today? Here. So this is what we mean by elasticity in this case. So in this case, an object which is matter returns back to its shape. So now this one has a high elastic properties, okay? Some materials, like this one, also has high elastic properties. I need a lot of force to really cause it to bend, okay? Water, on the other hand, if I put it apart, it's going to break apart. So water is not, does not have any elastic properties whatsoever. I know you were thinking probably differently, but that is basically the thinking. If the air, for example, I can push it away, part of the air went this way, the other part went that way. If I put a column in it, I will actually see the flow of the fluid, in this case, the air, okay? Okay, this is Hooke's law. Hooke's law basically says the following. If I extend this, if I pull on it with a force, it's going to extend. So the force I am pulling with must be proportional to the elongation, meaning how longer it is now. So if I expand with more and more force, that is actually how this is working in this case. So it's giving me the length, or the extension in length, how long it's longer now versus how much force in here. I don't have any force applied to it now, so it's sitting still by itself. So this is the natural length for it. If I pull on it, it's going to have more and more. So the more force I put on it. This gave scientists an idea. This is called Hooke's law. It's the name of the guy who discovered it, okay? So that's basically the guy who worked on this one. To basically, you have a spring in here, and you have the spring now calibrated, instead of by distance, by centimeters and how much it's stretching, it's calibrated actually by a measurement for the force. So this is actually how we measure forces. We use Hooke's law. So if you ever wondered, how am I going to measure force? You say, okay, scale. Well, scale works on Earth, yes, fine. Okay, you can measure, for example, weights, which is a force. But how are we going to measure, for example, a force applied on an electron, for example, proton? So in this case, you may think the only way that we can do this one is by spring and mass system, and that is acceptable. Because you can do this experiment independent of whether or not you are on Earth or not. And that is why this is important. The scale in here is important. Because if I have to do this experiment, for example, in interstellar space where there is no effect of gravity on this object, then in this case, obviously, it's going to work. It's going to give me, if I stretch it by an amount, I know how much force is applied to that object. So this is how we measure forces using Hooke's law. So in this case, this is Hooke's law. How much it's going to stretch depends on the stiffness of the spring. Because this is stiffer, requires more force to stretch it just this much. Well, then this one has a different constant. The value with which it's stretched, it doesn't require a lot of force actually for me to produce this one, whereas this one requires a lot of force. So this is a characteristic also of solids too, that they have stiffness in this case. It stretched barely. If I put another 50 grams, stretch more and more and more. And this is how we have this law, okay? Makes sense, doesn't it? So 10 centimeter spring extends 12 centimeter when 1 kilogram load is suspended from it. What would be its length if 3 kilogram load were suspended from it? It's going to spend 3 times as much. Okay. So its initial length is 10 centimeters. You really have to think of this one, okay? So initially, it was 10 centimeters long. When I put 1 kilogram on it, that means I put 10 newtons, by the way, because 1 kilogram times 10 meter per second, that is 10 Newton. So when I put 10 newtons on it, it's stretched by 2 more centimeters for a total length of 12 centimeters. So 1 kilogram causes it to stretch by 2 centimeters, correct? So now if I place instead of 1 kilogram, 3 kilograms is going to stretch, 3 kilograms is going to stretch by 2 more and 2 more for a total of 6 centimeters more. Because this law doesn't care about the entire length, care about how much lengths change. So in this case, length change for 1 kilogram is 2 centimeters. For 3 kilograms should be 3 times as much. So now it's 3 times 2, which is 6 centimeters. In addition to the initial length, remember, the initial length was 10 centimeters. So the total length for 3 kilograms should be 16 centimeters. Does this make sense? Oh, I'm sorry. Man, you guys need to tell me. How come this stopped? So this is the Hooke's law. Yes? It's the force is proportional. Okay, very good. Is proportional to the elongation. Basically, it's not proportional to the actual length. No, it's proportional to how much we're going to add. So if I add more and more weights, the length changes by more and more. So this is how much length initially it had, okay? So this is basically, now I have 1, 2, 3, 4, 5 of them. So this change in here is 5 times as much as this one. Okay, so to go back to the example in here, so the initial length was 10 centimeters. This is what they said, it was 10 centimeters long. So when we put 1 kilogram, it went by 2 centimeters. It grew by 2 centimeters to become 12 centimeters altogether. Okay. Now the question is, how long is it going to be when you place 3 kilograms instead? When you place 3 kilograms instead, it's going to stretch by 2 centimeters for every kilogram. So it's going to be 6 centimeters for the 3 kilograms. In a sense, in this case, its length is going to be the old 10 centimeters plus 6, giving it 16 centimeters. Here's the question of the day, the second question of the day. If instead I put 5 kilograms, okay, what is the new length? So I didn't put 3 kilograms now. I'm putting 5 kilograms instead. What is the new length do you think it's going to be? Any suggestions? Come on, guys. Okay, somebody suggested 20. Let's think now. 5 times 2. Does everybody agree with Miguel? The answer is correct. Okay. So let's see why that is. So initially it was 10 centimeters. And I know it stretches by 2 kilograms for every, by 2 centimeters, I'm sorry, for every kilogram I add. So I add 1 kilogram, 2 centimeters, another kilogram, 2 centimeters, a third kilogram, 2 centimeters, a fourth kilogram, 2 centimeters, a fifth kilogram, that's 2 more centimeters. So this is 5 kilograms. It's going to cause it to stretch by 2 and 2 and 2 and 2. That's for a total of 10 more centimeters. 10 plus 10 is 20 centimeters. Does this make sense? Thank you, Miguel. Does this make sense for the rest of it? Very good. So that's item 2 of the discussion today. Item 2 is what happened to the spring, if I instead of putting 3 kilograms, we're going to put 5 kilograms. Well, its new length is going to be 20 centimeters. Make sense? So this is item 2. So remember, item 1 has to do with the forms of matter in the universe. This is another property of solids, and that is tension and compression. On one side, it's going to extend in length in here in this angular displacement. So if you take an object, a solid, and pull on it very hard, it's going to stretch, okay? And if you push it again, it's going to compress. So this is actually true whether it's a spring or actually a solid too, okay? That's why in the construction business, for example, or roads or even trains, what they do in this case, they leave a gap because thermal heat temperature causes things to actually push against one another because they stretch by thermal by temperature, basically when the temperature rises, or they compress when the temperature go down. So these are some of the properties again of metals, okay, in general solids, not necessarily just metals, because it's also true for concrete, which is not a metal, okay. Obviously, suppose you drill a hole horizontal through a tree branch as shown. Where will the hole weaken the branch the least? Okay. There is a lot of stress on the top of the branch due to the tension, and there is a lot of stress on the bottom due to the compression, but in the middle there is nothing, or at least the least of which. So that is the answer to that, which brings the idea of arches and how you build them. So that's basically because, again, they're supporting one another, and that's how the buildings now will have stronger support, and you don't need as many pillars as you do in the in the other buildings. This is the St. Louis Arch, which is based on the same principle in here. This is not supported with anything, and actually the shape is some sort of a parabola in here. So this is more or less what we're going to be talking about, solids. Liquids, they're one of their properties, in addition to density, is pressure. So the two things that we distinguish liquids from one another is the pressure plus density. So what is the pressure? It's the force exerted per unit area. The unit for it is the unit of force, which is a Newton, divided by the unit of area, which is a meter squared. Well, there are this one is in SI units, is a Newton per meter squared, also is called Pascal. So the PA in this case stands for Pascal. But what you will see people, at least the weatherman talks about when he talks about the pressure, he talks about the millibar. That is actually another way of measuring the units of pressure, which is the bar. Also, they talk in terms of atmospheric pressure. The atmosphere that we're sitting right now has tremendous pressure sitting on our shoulders. Actually, right now, it's 101,000 pascals, or 101,000 newtons per cubic centimeter, per cubic meter. I mean, per square meter, I'm sorry, okay? So the atmospheric pressure is 101,300 newtons per meter squared. That is, you and I are carrying on our shoulders. It's a lot of weight, actually. And that is the weight of the air that is above us. So this one actually is called the 1 atmosphere. This number is actually Pascal. The same thing, okay? It's just an honor of Mr. Pascal, who did a lot of things in this area, okay? So it's a lot of pressure, okay? And we're used to it. That is basically, in a nutshell, what this thing is. In a fluid, it turns out the pressure is measured in terms of how deep we are in the fluid. Because if you go to this much depth in fluid, you have all of this weight above you. And that is the additional pressure in top of the atmospheric pressure. So if you go under a swimming pool, for example, in here, you're going to feel a lot of pressure coming from the weight of the air, of the liquid above your shoulders, above your body. So in this case, you're going to feel a lot of pressure. And the more you go down in the ocean, the higher the pressure, to a point that you will feel a lot of pressure coming from every which way, and you tend to be imploding in this case. You don't explode, you implode. However, if you go to the upper, for example, with no proper attire, you have to have a proper suit with covering to counterbalance the pressure. If you don't, that's what's going to happen. Same thing also if you go to the higher and higher altitudes, like for example, the Himalayas, you're going to feel and experience less and less pressure, as a matter of fact. And that is a problem too, because your internal pressure will be higher than the external pressure, then that will lead to the opposite phenomenon, namely the explosion in this case, where parts from the inside come out, unless you are properly either trained because of the fact that you're accustomed to it, or you have the proper suits for it. Obviously, when you go higher in the Himalayas, it's not a lot of height, honestly, to cause a lot of change in pressure, but it does, and you can experience it. Versus if you go under the oceans, which is because of the density of the water, is going to change rapidly, and how rapidly, we're going to talk about that. Again, when you stand on 1 foot instead of 2, the pressure you exert on the floor is going to be the same. I mean, because no, I'm sorry, it's going to change. So you have 2 feet now up. So if you weigh, for example, let's say 200 pounds, you have 100 pounds on this foot. That is the pressure on this side. You have 100 pounds on the other foot. If you lift one of them, your entire 200 pounds is going to be exerted on 1 point. So it's going to double, actually, more or less. Okay? Because again, in the area in here, you made the area less, that's all. So same thing in here. You can take I'm looking for a sharp object. This is a sharp object. Okay. You have 2 objects in here. You can push with your finger on this object and you can feel it, but not as much as if you feel on a sharp object. With a little bit of push, you're going to feel the pressure. So the pressure here is a lot higher because the area is a lot smaller versus this area in here, which is a lot wider. So the pressure is not much. As a matter of fact, I'm pushing as hard as I can, and I don't feel much because of the fact that there is a big area. So the pressure is very low. Here, I have to be very careful because if I push with the same thing, I'm going to puncture my skin in here. So this is the pressure. So the pressure has to do with the area. The fact that the area is tiny in here case leads to a higher pressure. Again, think of the expression. What happened here? Why it's not going in? I think I broke my probe. No, it's working. So again, think of this expression in here. Force over area. Once you make the area smaller, the pressure will go higher and higher. So again, pressure in a liquid and gas, both of them, force per unit area that liquid exerts on an object, depth dependent. The further you go in depth inside the liquid, the more pressure you're going to experience. Swim twice as deep, then twice as much weight of water above you produces twice as much pressure on you. Okay. And it acts in all directions. That's why you are going to feel the implosion, because you have very small, basically, profile that you're not going to see much difference in pressure between the outside and the inside, between the top and the bottom. Okay. Pressure depends only on the height. Look at this shape in here. You can prove it that doesn't matter which shape you have, the liquid rises to the same level because of the pressure. If there is more pressure on one side, it's going to rise higher than the other sides. But because now it really depends on the height, it doesn't matter which way you make it in here. There's more liquid on one side than in the other. But all of them have the same height in this case. So it only depends on the depth in this case, how deep you are. As a matter of fact, the formula for it is the weight density times the depth. So if you're ever going to be asked to do calculations, the weight density, which is just the force of gravity times the normal density, times the depth, how deep you are in the underneath. Okay. And this is the water tower, which uses the same principle to deliver high pressure liquids, fluid, water basically to homes. This is another idea of why the depth matters. An object in this case in here at this level has less pressure because this is how much weight it has to overcome, I mean, for this pressure, versus this point in here, which has this much weight on it. So the fluid that comes in here will come with a higher velocity because it comes with a higher pressure than the fluid in here. And the projectile that form in here has a less range than this one, because of this one has a very, very high initial velocity along this direction. So every particle of every droplet of water that is going to fall is going to have a higher initial velocity in the vertical direction than this component, because of the fact that this has less pressure than this point. Okay, so again, that is related to the depth and the size of the fluid. Buoyancy basically is another force in here that has to do with how much fluid basically is exerting pressure in here. It has to do with how much fluid is pushing from one side to how much basically it's pushing from the top. Obviously, this level in here is at a deeper level than this point in here. Hence, there is more buoyancy from the bottom than in this case. So in this case in here, there is the fluid will feel far more force pushing upward than from this side. So in this case, there is the net weight, net push upward. Don't forget that this object has its own weight. Plus this imbalance of the two forces, the two pressures that are on one side and the other, which are basically force divided by area, will result in a force that is pushing upward. And this is what we mean by the buoyant force, okay? So the buoyant force is the force that is acting against the weight. So if the weight is too much compared to the buoyant force, the object will sink, albeit slower. Okay, but it's going to go down. If the buoyant force is more than the weight, then the object is going to rise up and float. If they're canceling exactly one another, the object does not float, does not sink. You put it wherever you put it in the fluid, it's going to stay in that place. It doesn't rise to go up above the liquid, or doesn't go down and go sink all the way to the bottom. So that is an object that does not float or sink, because in that case, the buoyancy and the weight cancel each other exactly. Okay, this is what fish does basically. They don't have, I mean, if they want to go down, they will go down. All they have to do is change their density enough so that they're less dense, and now they go up. If they want to go down, they take more fluid, and now they're actually increasing their density, and now they go down. Okay, that's actually how submarines also work too. So submarines, they do take water. When they take water, they are going to be denser overall because they have already still metals and all the things, so they're going to start to sink. So if they want to rise, all they have to do is expel that water and make more and more basically chambers that are empty, and so they rise up. So it seems like the fish learned it from the submarines and how to go in and out of the water. Yes? Does that make sense?
Yeah.
Or is it the other way around? The submarines learned it from the fish, maybe. So is this technique developed first by the submarines or by the fish? Submarine developed this thing, obviously? Are you joking? Okay, Jacob is right. Okay, very good. So it must, that's how basically we learn. We learn to fly from looking at birds, and we learn to basically go underwater from watching how the fish does it and learning how the fish does it, okay? Again, Mr. Archimedes came up with a law that basically talks about this buoyant force, and basically he figured it out that the buoyant force is actually equal to the displaced fluid, the weight of the displaced fluid, okay? So all you have to do is just weigh the object before outside, attach to a spring basically, and see how much it's going to pull on the spring, and sink it in the liquid and see how much it's going to weigh. It's going to weigh less. If you fill the cup to the brim with a liquid, with a liquid before you put the object in, then it's going to, liquid will basically pour to another container, take that object and weight. And that is how you prove that the buoyancy is actually, the force of the buoyant force is actually equal to the weight of the displaced liquid. And it's the same regardless of how deep you are, because if you are this much depth, you're going to be pushed up by this much force from the top and the bottom. So then in this case, the difference is an arrow. If you are this much deep, in this case, you have more arrows on the top, but you still have more arrows on the bottom. The net buoyant force in here does not change, does not really depend on how deep you are. It depends only on how much you displace from this liquid, which is really proportional to the volume. That's it. It's exactly the volume. So depending on how big the object is, it's going to displace the equivalent amount of that fluid above, and that is how you get higher and higher buoyancy. That is how you actually have boats float made out of steel, which is a lot denser, and I just argued earlier that it's a lot denser than a liquid, yet it floats. The reason why it does is because of the fact that it displaced more of its own weight of ocean. So if you take a boat, a huge boat, for example, for commercial lines, those big boats, and you put it on the ocean, it actually moves the ocean a little. And that little is just enough to compensate for its own weight and stays afloat, okay? Because they make the shape of the boat in such a way that it displaces fluid. If you take that same amount of steel and make it into a block and put it in the ocean, it's going to fall straight through. So that is really why boats can float and can actually travel in the oceans. So again, I talked about sink or float, and sink is when the weight of submerged object is greater than the buoyant force. Neither sink nor float if they are equal. Float when the weight of the submerged object is less than the buoyant force. In this case, the object will go up. Okay. Mr. Archimedes supposedly was taking a shower one day, and he came out naked from his bathtub, claiming "Eureka, Eureka, Eureka," and that's how he discovered this principle of buoyancy, basically. Okay, it states that an immersed object completely or partially is buoyed by a force equal to the weight of the fluid that is displaced. So this is an important principle. Okay, so you guys in this class, you really need to remember this principle, and that is item 3. Is to state it in your own words. State Archimedes' principle in your own words, okay? If it's on slide number 34, okay? And this is true whether it's a gas or a liquid, okay? For both of them. A lot of this discussion is the same, okay? So we're not going to be repeating it in the case of gases, okay? Because it's the same thing. So again, I talked about how much you're going to have in here, how much weight. So what you do in this case, you weigh the object before it weighs 3, whatever that is, 3 newtons, for example. When you submerge it now, you see that it weighs 1 Newton because of the buoyant force. You take the fluid that has been displaced and you see it's 2. So this is basically in a nutshell how we do the experiment. And we used to do this one when we were live. So a lot of this discussion points are about Archimedes' principle. Hopefully you guys can look at them. So this is again what I was talking about, boats. If you take the entire boat and make it out of iron and make it into a solid object, it's going to sink for sure because its density is much, much higher than that of the ocean. So it's going to sink straight through and through because the buoyancy in this case exists, but it's not as much to compensate for the weight of the iron or steel. But if you take that steel now and deform it a little bit, now it's going to have this to displace this volume of fluid because of its shape. This is the volume that it's going to displace. Although you don't notice it, but there's actually slight rise in the ocean every time a new boat is basically put on the ocean. But so, because the oceans are so huge, okay? And these boats, no matter how big they are, they're still a fraction of that size. So you're not going to, it's an immeasurable quantity, but it's still there. And that is enough for you to compensate for the weight of the same iron by the buoyant force because the liquid displaced in this case is huge. So in this case, the boats will float and then you can continue. It's a fun problem actually when we do this class with calculations to see how many containers, how many objects that you can put in this object so that the onset of sinking, basically where the top of the boat will just barely be above the liquid, above the sea level, okay? Any more thing, a hair or a piece of feather will fall, will cause the whole thing to go down. It's a fun problem. okay? All you have to do is just see how much liquid versus this entire volume, not just this volume in here, okay? I'm sorry, the weight in this case plays a role versus the entire volume, yes, okay? It's a fun problem. So all of this is about the same thing in here. This is about fluids that float or the sink. In this case, fresh water is salt water is slightly denser than fresh water. That's why people actually tend to float more easily in salty water, like for example the Dead Sea, than in the case of regular fresh water, which has the density of 1 gram per cubic centimeter. The gram per cubic centimeter is a convenient unit of measurement, by the way. A very convenient one. Instead of talking in terms of cubic meters, where the numbers are in the thousands, it's much easier to use the grams per cubic where the numbers are in single digits. So in that case, iron is 7.8 or 8 grams per cubic centimeter, okay? And again, it applies to air, as I was talking about in here. If you fill up a balloon in this case and you heat it up, as you do heat it up, its density changes to such a point that it displaces its own volume of the air around it, and this one rises, okay? And this one starts to rise. If you deflate it a little, then in this case, it's going to lose some of that volume. And when it does, it's going to displace less and less, and this starts to come down. So again, we talked about this point in here. It's the object, the volume of the object, and the volume of the fluid displaced. So to go back into the same thing in here, for example, for the issue of the boat, it's really not how much mass you have in here. You can have those boats carrying a huge amount, and they're actually the main means of transportation of goods between in the oceans. And they're big, they're super big, much bigger than any plane that you can think of, yet they float. So it's not really the amount of matter, but rather think of in terms of the shape, okay? When we do Physics 11, and I think next semester we're going to offer Physics 11, there is a lab there that they used to offer where you actually build your own boat at home. And you share your design and actually the fun with it too, okay? And see how much you load on it before it starts sinking. Do that in your bathtub. So hopefully next semester is going to be offered, and we'll have more fun then too. So again, 3 rules. An object more dense than the fluid in which it is immersed will sink, like for example iron. An object less dense than fluid in which it is immersed in will float. An object having the density equal to the other object will not either sink or float, okay? So this is actually a good way of measuring density, okay? And this is Pascal's principle about the pressure, the fact that the pressure is moves uniformly throughout the entire liquid. So if you change the pressure from one side, it's going to express itself in every other point in the liquid, okay? This is actually gives us an idea where we can actually build something called a hydraulic press in this case. If you have a 10 kilogram in this case, it's going to, on a smaller area, it's going to exert a force. Let's say, for example, this is a square meter, okay? Or let's make it smaller. Let's make it 1/10 of a square meter. Obviously, the pressure in here, it's 10 kilogram times 10 meter per second divided by 0.1. So this is going to be equal to 1,000. Because 0.20 divided by 0.20 multiply. So this is 1,000 pascals, okay, just to illustrate the point. 500 kilogram in here, I can lift it with the same 100 kilogram. All I have to do is just push 10 kilograms, I'm sorry. Let's see here the math for this pressure in here. 500 times 10 divided by an area, so that this is actually 1,000. Obviously, the numbers cancel, and this question mark will be just 5 square meters. So 5 square meter area in this case will cause the same pressure as this one, because 500 divided by 5, that's 100. And 10 divided by 0.1, that's still also 100. So it's the same pressure on both sides. So think about this one. You can lift an elephant if you like with this hydraulic press. You can lift whatever you want to, okay? So this is actually a machine. This is a simple machine. It's like the lever. It's actually used in the industry in here to lift heavy objects like cars, for example, okay? And the same principles of hydraulic devices are used in all kinds of instruments like this one's in here. You can see this is actually a hydraulic system in here. And it's actually used also in the braking of trucks and so on and so forth. Surface tension and capillarity is also another property of liquids because look, the liquid every which way, inside there is those forces that I was talking about in the beginning, like van der Waals force, for example, in the case of the water. But when it comes to the surface, in this case, on one side there is no force, which is the surface on the outside of the surface, and there is force from underneath. That creates surface tension, which deforms the object on its sides in here, okay? And that creates this shape in here, this U shape for the liquid in here in this case. Okay, this is called capillarity in here, and this is due to the surface tension. So it's another force outside on the object. This is the one that causes the droplets of water to be more or less have that spherical shape. Okay, gravity does it for big object on big scale, but this one does it on smaller object on smaller scales. Okay, it gives them this force and this shape and spherical shape. Here is what I was talking about in here. This is the interaction, albeit it's for something they call short range interactions. Basically, the molecules of the water interacting only with their neighbors, but they interact every which way. On the surface itself, they don't have water molecules above them to interact with. So they put on this side and that side, of course, the ones on the bottom, but on this side, and that is what creates the surface tension, okay? If you try to break the water, you're going to feel that surface tension, okay? Take a sharp needle and try to see it, and you see that it really requires some force in there to break that one. And that is the surface tension that you have in there. And if you pull on it, it's going to come up like this one, actually. It's going to pull on this object too. As a matter of fact, it's going to pull a little bit of water, and this is what we have, a capillarity. Capillarity, this depends also on the size of the surface in here, okay? Depends on the size of the surface in here. The smaller it is, the more it's going to pull on this than the other one. And again, it has to do with surface tension again. Okay, which brings us to the last point in here in gases. The fact that I mentioned at the beginning, the atmospheric pressure is the weight of the atmosphere that is above us. And that is what I was talking about, 101,300 newtons per square meter. That is actually the pressure, the atmospheric pressure. And this is the one that we're submerged in. We live in it, okay? So we're used to it. Or 101 kilopascal, kilo cent for 1,000. So it's roughly that much. So it's 100,000 newtons per square meter. So if you think that you cannot lift 10,000 kilograms, think again, because you do on a regular basis. As you're sitting right now, you're lifting about 10,000 kilograms. That's about 20 tons. That truck that is outside there, I mean, the 18-wheeler, that weighs actually about maybe less than that, but that's how much you're actually carrying with you all the time. But we get you accustomed to it. We're used to it. If we go in a place where there is the pressure is actually higher or lower, we're going to experience some problems that we need to adjust with. For example, if we go on Mars, where the pressure is a lot less, about 2% the atmospheric pressure on Earth, we're going to have very major problems because our insides will come out again, because the pressure outside is a lot less than the inside. If we go, for example, under the surface of Venus, which is going to have actually another problem, which is the temperature, the pressure there will be so high. Ignore the temperature for a moment, but the pressure will be about 90 times the pressure on the atmospheric pressure. Again, we're going to be compressed to basically smithereens because of that amount of pressure. So this is the idea that you really need to think about. Which brings me to an interesting point in here. If you go under the ocean, 10 meter, which is about 32 feet, you're going to experience another additional atmospheric pressure to the already existing atmospheric pressure above coming from the air. If you go 100 meters, you're going to be under almost 10 or 11 atmospheric pressure altogether. That's 10 atmospheric pressure. No one can survive that much pressure without proper equipment. It's going to be too much. It's going to crush you inward, okay? If you go kilometer under the water, and there are animals that live around that, actually they're deeper than that, the atmospheric pressure is 1,000 times, okay? For sure. you're not going to survive it unless you really have to have proper equipment, a submarine or something like that. Even submarines that deep is too much, okay? Too much pressure for them. Here is, how many questions do I have so far? 3. This is the 4th question of the day. How does the fish do it? By the way, the deepest points in the oceans can reach about 10 times this much. It can be about 10 kilometers or more, 11 kilometers. How does a fish do it? What do you guys think? Because we cannot survive it for sure. Take an elephant, it's not going to survive it. Internal gases? What do you mean by that? How does a fish survive that much depth? And we can't. An elephant cannot. Whales cannot actually cannot survive that much depth because they cannot breathe. They need to breathe air. Actually, whales are actually mammals. They breathe air too. Air sucking into their stomach. Is that how it works? We can take air with us too. Do you think that's gonna help? You're almost there, Jacob. It's almost the answer. Guys, everybody else, this is not a democracy. You really need to participate. You need to give your ideas. Why do you think the fish survive that much depth? And I was just telling you 1,000 atmospheric pressure is too much for us to survive. We cannot survive it. No, this is 100. I'm sorry. Did I say 1,000? Yeah, when it is 100 meters, it's 10 atmospheric pressure. When it's 10 times, it's still 100, which is way too much. Okay, so I was a little bit wrong. I don't understand Zena also because he said something and I don't really quite get to the correct answer yet. I want to understand. Let's say, for example, you go 1,000 meters, which is a kilometer under the ocean, okay? They are more dense than us. That's a good way of thinking about it, except that's not true. Because have you ever felt the fish in your hand? You can squeeze it, can't you? So it feels kind of made up of a very soft material. So if they have less air, then that's a problem because then they're going to go up. Deep sea fish don't have. Okay. Let me tell you their secret, okay? That's all right. You guys are all hovering around the answer, okay? Let me tell you where their secret is. Their secret, they breathe the water. So their inside pressure is the same as their outside pressure. So the two pressures cancel, that's all. So here is a fish. This is my best rendition of it. It takes the water in and pushes it out. So in this case, its internal pressure is the same as the outside pressure. So there is no reason for it to implode in the explosion. Same reason why we are also feeling okay under this much atmospheric pressure is because we breathe the air. So our inside pressure is 101,000 basically pascals, and outside pressure is 101,000 pascals. So we're basically neutralizing, so we're fine. Does this make sense as an answer? Okay, very good. That's because the fish breathes the water. So that's your answer. If you want to survive that much deep in the ocean, all you have to do is just breathe the water. Just breathe it in like you breathe the air. Make sense? Okay. Can you though? That's another challenge, okay? Okay, very good. So this is the fourth item of the day today, namely that how does the fish survive? Depth of the oceans is because they simply breathe the water, just like we do in here on the atmosphere in here, where we are fine, okay? Obviously, if you take that fish and it's not adjusted, it's going to really feel a lot of pressure and they're smashed inside because of the, I mean, the opposites, okay? So they don't survive it. Here another challenge, how are we doing on time? The 101,000 atmospheric pressure, 100,000 basically pascals, is equivalent just about 10 meters. That's exactly what I was saying, 10.3 meters. That is the argument I was making earlier, okay? That is because the density of water is about 1,000 times bigger, okay? So if you take this one and cancel 1,000, so you'll be left with 101 pascals, and the density of water, I'm sorry, the value of G will remove the one of this newtons. So this is the depth that you'll be left with. Basically, it's about 10 meters, okay? The density of air is not exactly 1 kilogram per cubic meter. It's 1.3 or 1.23 or something like that, kilogram per cubic meter. That's what makes that difference between the numbers in here. That's what makes that 0.3 changing in here in this value. No matter how much power you have, you can never drink from a well that is more than this depth, 10 meters, 10.3 meters, because that's a maximum that you can use non-mechanical or mechanical device to really bring the water from that depth, because that's going to rely on the atmospheric pressure. So in order to pump water or oil or anything like that from depth more than 10.3 meter, you really have to use a non-mechanical device, like for example, other mechanisms, okay? Or have it pushed by underneath by some sort of a high pressure other devices in there. But if you're relying on a mechanical device, it's not gonna work. So the maximum is gonna be 10.3 meter. Barometer is a way of measuring pressure. So if you take, for example, a liquid in here, it doesn't matter which, for example, alcohol, and you fill it to the cup and then you put it back onto it, it's going to push, the air that is going to be pushed in here will be equal to that much weight. And you make the graduations in here, and now all of a sudden you are measuring actually the pressure. So this is called the barometer. This is not the only kind of barometer. There are other types of measuring pressures like this one in here. It's also using a different mechanism to register the pressure. At a fixed temperature, Boyle has found that the pressure and the volume are inversely proportional. In other words, if you increase the pressure, the volume will go down, okay? So this is at fixed temperature. This is true for basically low density gases. They're called later on ideal gases. So this is the relationship, by the way. PV equals to PV. This PV pressure measured from this device with this volume, which is big, the pressure is low. When the volume went down, in this case, less volume, the pressure went up. So this is basically what Boyle's law is. Buoyancy in air, I already mentioned the fact that it applies to for both liquids, whether liquid or fluid. And this is actually a slide from previous liquids. Bernoulli's principle is a very important idea that we're going to really explore. And that has to do, first of all, with the flow of liquids. So this is not actually hydrostatics, but more of a hydrodynamics. So a streamline in this case is what we call a laminar flow. So what happened in this case is the flow is moving in here with the velocity over this big area, whereas in here it needs to move with the smaller area and you have to squeeze the same amount of water through it. So the velocity here must be bigger for smaller areas. And you can experiment with this one with a hose, for example. If you come to the one end and you push around it, and you will see the flow comes out very high. So this is actually the conservation of matter in this case, because the amount of fluid that passes this area must be the same amount of fluid that passes this area per unit time. And because this is proportional to the velocity, this one also is proportional to the velocity, but because the area is less, so if there is a certain number of cubic meters of fluid that pass per unit time, it has to go the same thing in here. But the area is less, therefore the velocity has to be higher to compensate for that. Okay. There are two types of flow. There is a laminar flow, the one that is smooth and non-turbulent, basically, and this is at constant speed and so on and so forth, constant density of flow, I'm sorry, versus turbulent flows, like, for example, what happened in a tornado or very high, basically, velocity phenomena. Bernoulli's principle actually applies in the following way. When pressure is increased, what am I here? And the velocity in here is going to be decreased. So this is the velocity squared. In addition to that, you have actually also how much height difference in here. So this is the equation that explains, among other things, how liftoff of plane happens. So in a plane, this is the wing of the plane, how it's made up. So what you have in this case, you have the flow of the fluid underneath the liquid, underneath the wing, whereas there is another flow of the air above the wing. So in this case, the wing acts to deflect the air above, but the air in this case is at calm before the plane passes by, and after the plane passes by, it's calm also. So these points are similar before and after. So this is the same point actually before the plane passes through it. So what happened in this case, this flow in here must happen at extremely high velocity versus this one to reach the same point in the same time at the end. So this must travel faster than this one. So resulting, since this velocity is higher on this end, high velocity, this one actually is low velocity, which means this Bernoulli's expression really has to do with the conservation of energy. So in this case, the pressure has to be low in here. P is low. I'm sorry, P is high pressure. The reason why is because the velocity is low, and this number does not change. The sum of these two doesn't change. So in this case, the pressure is low because we have high velocity, and that difference in pressure, because the pressure from the bottom is higher than the pressure from the above, and that's what causes the plane to lift off. If you take this wing and reverse it and put it backward and put it on NASCAR cars, basically in that case there is a higher pressure from the above to the bottom, and that's what keeps NASCAR cars on the ground. Otherwise, they will take off. Okay, so the same wing can be used to hold an object in place or to use it backward, and that is using Bernoulli's principle. That too is used actually for the curved ball in baseball too. So that is how this also explains that too. Okay, this experiment I used to do, but unfortunately we can't, I don't really have a setup for it. Basically, if you blow on a piece of paper from the top, it's going to have wind that is blowing at high speed, meaning the pressure is below, and the pressure in the bottom is not changing, so the paper will bend upward. If two trucks, for example, are moving next to one another, one against one another, so the flow between them will be at a higher speed, meaning the pressure is low, so they're going to be pushed against one another. So these are all examples of Bernoulli's applications, okay? And this is what causes the roof actually to take off, because again, there is a high wind on the top, which means the pressure is low, versus from inside where the pressure is high. So this causes the roof in this case to come out. Perfume atomizers are also used in the same principle and same idea also. So when you pressure on the atomizer, the air will come out super fast, causing a depression, and that depression will cause the fluid to come out from the perfume, and it mixes with the air and it comes out. Okay, so all of this are examples of Bernoulli's equation, which is a very, very important one that can explain, among other things, how planes take off. Finally, plasma state, as I mentioned it before, is the fourth state of matter after solids, liquids, and gases. Plasma in an electrified gas, the amounts that make it up are ionized, stripped of one or more electrons. So this is basically what one of you guys mentioned in terms of the fact that it exists in the sun and the flames and a lot of other forms of matter because of the ionization. The sun and other stars contain plasma. The aurora borealis also and australis are also, both of them are examples of plasma because extremely highly charged particles come from the solar wind. And once they're trapped in the magnetic field of the Earth, they spiral down either northern or southern, depending on their charge, and depending on their mass, also how deep they are going to be in the atmosphere. And they cause the atoms of the atmosphere to be ionized. So that is actually a plasma state too. Fluorescence and all of the lighting basically uses the same principle. And it's used actually in TVs. Modern TVs use also plasma technology to basically produce images with specific frequencies, and they are a lot sharper because you can actually have the image with extreme high definition details than what you do in the old day in the fluorescence, basically when an electron hits the screen and produces a fuzzy image in there, and another electron will hit another portion of the screen or the same portion of the screen, but actually it's a different depth, and that's going to produce another color, resulting in the 3 RGB colors that give you all kinds of different colors. But for this one, actually, it's going to produce high resolution images with varying values of the colors, namely, and that is basically why the different shades of color appear a lot sharper than in the case of the old fluorescent screens. Okay. So this is in a nutshell your entire chapters, 3 of them. I thought it's going to be hard to do. I'm glad we finished it all. And I think we have an exam coming. So I'm trying to think maybe we're going to change the contents of the exam because of the fact that we have the spring break that is coming in about 2 or 3 weeks at most. So I'm going to see maybe the midterm will be pushed to the week of the actual midterms where everybody is having midterms. And I will be on campus with some of the classes that have midterms in campus. I have 3 classes. They're calc-based classes where the college has required us to have them administered on campus. So during that time, I will have probably, you guys also have your online exam on Canvas during that time. So that's where I'm headed with this one, so that it's going to be manageable for me to be on campus, and at the same time you guys are taking the exam, so I can access the questions that you have during that time or later on. Whereas if we are going to have lectures at that time, it's going to be hard for me to come from campus to here. And actually some of the exams are scheduled during your class time by the college for the other classes. Anyway, so that is where I'm headed with that. I will keep you posted on the date. It's most likely the week after the spring break. And it's going to be either a Tuesday or a Thursday, one of those days for the exam, for the midterm. And the chapters are a little extended, of course, to cover more materials in there. So again, you will have a review for the midterm. The review is going to be graded for participation. Regardless of what you score in the review, you're going to get the entire grade for it as you do it. That should to show that you have taken the exam seriously and you're preparing for it seriously, and you'll get full credit for participation for just doing the review. Now, the actual exam is a different story, so you really need to prepare for it and have it ready. Make sense? Okay, watch for more details if it doesn't make sense to you guys. Okay, let me stop the recording right now because still we have 1 minute, I think. And it's just in the nick of time.